the big revolution which is happening around cooling is about liquid. And Mark introduced is the chip-to-chiller story. So how we can address this enormous revolution. And that's a revolution which starts from the server, which starts from the rack, evolve to the pod, move to the building, and finally consider new campuses, liquid cool racks. And the final point is that all of those are definitely part of full story. It's part of how we power in and how we reject all this power to the heat rejection unit. So Schneider is approaching this story as an end-to-end approach, considering how to power and how to reject the same load, which is growing. On the cooling perspective, on the heat rejection perspective, having a deep dive on that, it is primarily focused on having an end-to-end approach. Liquid cooling and cooling in general are around since a while. Liquid cooling in particular is available since a decade. But the key point is that many different players are looking at one single angle, one single perspective, while at the end of the day, the different parts, different components of the cooling architecture are part of an end-to-end approach. And if you are not looking at an end-to-end architecture, it is not possible to optimize the end-to-end approach, offering a better sustainable, a more efficient, and more AI-based data center. So, first of all, this is not something related to a single part of the game. As I said, end-to-end. End-to-end means large portfolio, wide portfolio, because unfortunately, liquid cooling and cooling in general is not something related to a single magic tool which fixes everything. It is the combination of multiple different parts of the offer which need to be combined together, adapted to the application, adapted to the end user, adapted to the load and to the location to optimize it. So how we can recombine all of these is the key. So we at Cooling for Schneider Electric believe that this portfolio designed in our different cooling hub we have across the globe and manufacturing in different facilities we have is able to provide you the final solution to maximize the efficiency. So all our technological centers and our facility across the globe are oriented, specialized in providing the final solution, testing the final solution, looking at how we can do this. But why we are migrating? So we are doing product, we are doing offer, we are having a supply chain, we are integrating all of those, but why? Why we should not stay with air-cooled data center that everybody knows and how we need to migrate? The point is around densification, and Mark went through this. So the densification and the evolution of the AI is certainly moving to a completely different story. And is also sharing a different approach of where we are. So looking at the different capacities or the different densities, there are different solutions. And some of the numbers here, we may probably argue for a couple of hours, if it is really 40, 45, 50 kilowatt per rack. But really, looking at this evolution, there are two big areas where air and liquid coexist, and where liquid cooling is mandatory, period. In between, and that's not a technological choice, but primarily a choice coming from the ASHRAE guideline, there's the 50 kilowatt per rack threshold. Why there is a 50 kilowatt per rack threshold? Because below 50 kilowatt per rack, you can use air cooling. It is pretty efficient solution, air cooling for that, but back in 2020, ASHRAE introduced a new guideline mentioning that at 50 kilowatt per rack, the air temperature, the supply air temperature, to dissipate server for more than 50 kilowatts per rack need to move to 21, 24 degrees Celsius. Lower than that can be 27 as recommended. 50 or above, it must be 21. 21, on the cooling perspective, is not sustainable anymore. Neither on the power availability, nor on the sustainability, nor on the CapEx and on the OpEx. So that is the real dead end of any air cooling, not just because of the technology, but because the guidelines are saying that the conditions are not applicable anymore. Less than that, you can use liquid. Absolutely, and we will see later how. More than that, you must use liquid. And now, looking at what NVIDIA is doing, looking at what the AI is doing, the transition is moving from the current densities that is 50, 15, 10, 20 kilowatt per rack, so more on this area, to 130, 140, 200 kilowatt per rack. So we are rapidly moving in that direction. So we are rapidly moving to the adoption of liquid cooling. So again, what is liquid cooling? And again, liquid cooling is something that is well known since a decade. And even if you look back at 6 months, 1 year, 2 years ago, many companies was promoting liquid cooling as a no-fare, as a single product, is a single magic product which can fix all the problems. The reality is that liquid cooling is not a product. Liquid cooling is a complete architecture which certainly starts from the liquid cool racks. But these liquid cool racks, these liquid cooled servers, are part of the entire ecosystem, which include distribution, complementary air, and heat rejection. This is liquid cooling, not just what in the server or what is in the rack. So in order to have a optimization of the architecture, we need to look at the entire architecture. We can summarize this architecture in 3 main pillars and 3 main areas and look at each of those, how to optimize that. There is what it is in the white space. There is what it is outdoor, which rejects heat, and what it is in between. And each of these 3 portions need to be adjusted, optimized, but designed together. It's not anymore the design that involves just one of these 3. We need to consider holistically the entire end-to-end approach, both on the sustainability but on the technology perspective. So let's focus on, let's zoom in the white space. What is going on in the white space? What is the main guidelines for the white space? Starting from the server. And again, looking at what is happening, what happened and what happened inside the racks, inside the server in the last 3-4 years is extremely interesting. 1 year ago, 2 years ago, on the technological perspective, and still now, there are different technologies for to cool a server with liquid. And we can summarize those according to 2 vectors. One vector is where the fluid is, and the second vector is which fluid is. So if the fluid touches directly the server, it is immersion. If the fluid does not touch directly, but there is a plate in between, is direct to chip. And then if the fluid, like water, does not change state, is single phase. When it changes states, it is 2-phase. According to this mapping, all the different solutions, immersion cooling, 2-phase, single phase direct to chip, 2-phase direct to chip can be more mapped. And again, on the pure engineering perspective, looking at these 4 corners, all of those have pros and cons. And all of those were very valid and are still very valid alternative on the pure technological perspective. However, it's not a matter of technology also, only. It's not a matter of only technical decision. It's how this technology can be integrated in a data center at scale. And the only way to do this currently is using primarily direct-to-chip single phase. And this is, again, not because only the technology. It is true that direct-to-chip single phase cold plate, it is embedded in the server. So you can buy the server with the cold platings in. It uses water, so it does not impact on any regulation with the refrigerant. But the three major points are, it is simple. You can buy it liquid-cooled server as you buy an air-cooled server. It can coexist with existing data center where there is air-cooled server. So it is easy to go again. And it is compliant with the AI because cooling the chip directly is very effective on the heat rejection unit. So these topics that are not only technical challenges, technical possibilities, are driving as way one at scale of liquid cooling, the cold plate single phase. Is this going to happen forever? Probably not. But today, all the other technology available in the market are and remain niche application for engineering, supercomputer, and other applications. But on the scale approach, that's the solution today. And so when we look at how to do an architecture, the architecture needs to be considered with this approach. And to fit this approach, we need to consider, okay, what else than the rack? We look at what in the rack is. What else than that? First of all, how to distribute fluid. So there is in any liquid cool architecture, the two circuits. The circuit that goes to the server is called a TCS, technological loop. This TCS literally moves the water inside the server. So at the first glance, people can say, okay, it is a couple of manifolds, couple of pipeworks, and everybody are happy, so not super complicated. Unfortunately, this is not just like that. So a design around the TCS includes the manifold on the back of the server, on the back of the rack, which distribute the fluid. It includes the valves to regulate, the monitoring system. All of these are part of an architecture, which is not only related to a specific areas, not only specific pipeworks. So that's a full architecture again, and that's an architecture where many guidelines and recommendations are happening. ASHRAE just released a set of different guidelines. They are working since a couple of years. We had a release on early 2024, another release on late 2024, and more discussion a couple of weeks ago, 3 weeks ago, on the latest seminar. They are defining how to do the TCS, which material, for example, stainless steel, which kind of fluid to use, again, PG25, regardless you are in a very warm climatic condition, you must use glycol inside. However, you need also to check how to prevent biological pollution, biological contamination, because these at factory, during transportation, and during installation may happen and may impact severely the server. So again, even on the execution, is not just a plumbing application. You cannot buy the manifold, leave on a storage area, and for a couple of months, 3 months, 6 months, whatever it is, and then install it. No, it is something that is more on a pharmaceutical or chemical application. We need to prevent this. We need to be sure that it's happened. It's not just, again, a couple of pipeworks. And then that's an area where we are still working with ASHRAE to define, for example, how this impact on the coastal zone. where you leave the pipeworks and perhaps humidity with salt remain inside the pipeworks, and these pipeworks goes to the water past these pipeworks goes to the server or other stuff. So it is an ongoing application that all the community is working. So the TCS is much more articulate than what it looks like, and that's where we as a community, we need to work, Ashra in particular, with the server manufacturer, we as a manufacturer, but with the specifier, the consultant, the contractor, the installer, all together, because it, again, is not just a couple of pipeworks. And last but not least, the cold plate direct to chip cool the chip, which means that everything else in the white space, in the rack, in the system, need to be air-cooled. So air remains in the equation. There are no discussion around that. Of course, the percentage is much less than the full percent that we have today. However, we cannot under-evaluate this, because there is, in parallel with this single-digit or teen double-digit percentage, we need to combine with the densification. And densification is moving the capacity, the density from the current 10, 15 kilowatt per rack to 150, 200 kilowatt per rack. So if today with air cooling you need to dissipate 15 kilowatt per rack, even if you remain at 10% of 150 kilowatt per rack, you are at the same level or above the level of air you have today. So air remains in the equation, and remain in the equation at the same level or more than what it is today. However, it is a different kind of air. We need to likely cool the server in a different way, with different temperature, for example. Let's imagine to have a fully liquid deployed data center. So all the chips are liquid cooled, all of them. If so, what you need to dissipate is the thermal load of the electrical part. But the thermal load of the electrical part does not follow the Ashra recommendation. The Ashra recommendations are for the chip. So what is the water temperature there? The air temperature there? The air temperature was 27 as a supply air, but when you're looking at the electrical portion, it could be 30, could be 35. So we need air, but we need air designed at a warmer temperature. We need air, but we have, and we will see later, the CDU to distribute the flow. So we don't have so much space on that. So again, we need probably to look at a different form factor. Rear door heat exchanger, for example, are part of the game. So air is definitely entering, remaining in a different form, and in between, from now and the full liquid architecture, we need to consider that there will be plenty of data center in hybrid mode, where air and liquid need to coexist. So all these things say that, again, air is part of the equation. Moving out from the data hall, in this journey from the chip to the chiller, certainly one area that we need to consider is what is in between, what is the backbone of the liquid cooling infrastructure. And we can argue that all of those are essential devices. However, the backbone, the interface between the liquid cool server and the heat rejection units is the coolant distribution unit. The CDU, and we can argue that there are plenty of different CDUs, but in a very high-level perspective, the CDU is that device that allows the connection from the server to the heat rejection. You can do this with air and liquid, with liquid and refrigerant, with refrigerant and water, with water and water. All of those are CDUs, all of those. The primary application today is liquid to liquid, is water and water. So something like the picture on the right top part, where you have an heat rejection unit which move the water on the facility side, and the CDU which move the water into the server. Then this can be floor standing or in the rack. If for whom was at the cooling booth earlier, you saw that there is both the solution, both of them in the rack or in the floor standing are CDUs. And the main purpose, these CDU are essentially to divide the facility water and the technology water. Why? Why we need to separate? Because we need to keep under control the temperature, the pressure, the quality, the filtering, and the treatment of the water on the TCS. The TCS need to use glycol, stainless steel material, control of filtration, control of the water, control of the pressure, control of the temperature. So the CDU is this backbone. However, the CDU is a portion of the system. So when we look at what is the best choice to select the CDU, one point that we need to consider is what is the difference in temperature, or better, what is the approach between the heater ejection and the AT equipment. And the difference there really drive everything there. Example, you may have 6-7 degree approach. In that case, the IT equipment work, and that's an example, at 30 degrees C. If so, the system works. It works at 27, you have 20 degrees Celsius the chiller, that's the CDU. If you get the CDU, which allow a much closer delta T, so a better approach, 3-4 degrees Celsius, the IT equipment remains the same. What changes is the chiller side. And the real driver, the real big elephant in the room, when you look at the efficiency level, it's the heat rejection unit. And every single degree Celsius you can raise up the temperature at the chiller, you get 3% more or less in efficiency. So it is true that having a CDU with a very low approach, it is probably and likely more expensive. The CDU need larger pump, so power consumption is much higher, and the unit is heavier, larger. However, accepting that, the full end-to-end architecture is 10–15% much more efficient. So again, if you look at only a small portion, only the CDU, why we need to select a very small approach CDU? Again, it is more expensive, it is more heavy, it is larger, and it is more have more power consumption. But when you look at the end-to-end approach, that's completely different. And looking at the big elephant in the room, let's move to the final portion of that. So what about the heat rejection unit? And what about the chiller outdoor? Or which kind of chiller you need outdoor? So there are several different ways to combine the heat rejection with the CDU and the CRA. Those are few examples. We have a reference design you can download from our website where you can combine the different solutions. However, regardless the technology you are looking, if you have two chillers, one for cooling and one for air cooling, or the same chiller with the same loop, or the same chiller with a series loop, regardless this, the main driver is what is the temperature for the server. And that's the question number one everybody in the ecosystem has. And unfortunately, there is not a clear answer on that. Ashrai tried to answer, but they did not answer. Ashrai said it is up to the server manufacturer to determine which is the temperature. So they classify the server according to some classes, which is called S, like silicium. And these classes depends on define when and how to design the chiller and the heat rejection unit. The problem is that in many cases, when you design a data center, you don't know which server will be installed. So you don't know which class you need to consider. And the key point is that the S-class depends on the density. So looking at the density, and that's just an example, there is a rule. The higher the density is, the lower the temperature must be. So, and that diagram depends on the server technology, the cold plate technology. So don't consider this as a golden rule that a 600 watt per chip you can use S45. No, this is a general indication, but the final decision is on the server technology. Looking at this example, you can identify three major areas. The area where we have low density, similar to where we are today, so something around 400, 500 watt per chip, which means 15, 20 kilowatt per rack, where the water temperature can be much warmer than what you use for air cooling today. So it's certainly a great way to decarbonize. If you have a low density and you want to use liquid instead of air, the data center power consumption goes down dramatically. It's a pure decarbonization. And everybody would be great and happy if the density remained there. But the problem is that the density is going to move. And the more density you have, the lower the temperature will be. And you see that at more or less 50, 60 kilowatt per rack, you may are at 30 or 25 degrees C. So on the long run, you might have water temperature even colder than what you have today when you use air. So here, it is decarbonization. There is more sustainable growth. There are no way to cool those servers with air. No way. The big question is, and what else? Are we still going to reduce the water temperature? Or should I now consider the minimum water temperature at 30, just added the 25 and 20, and discussed 2 weeks ago about 15 and 10. This means to have a chiller outdoor rated to provide water at 7 degrees Celsius. 7 degrees Celsius was the usual temperature in data center 20 years ago. So that's clearly something that on the long run is not sustainable. So very likely, either we find a better way to exchange with better cold plate, or when we are in the red area, something new will come, like two-phase direct-to-chip or other technologies. Simply because it is not sustainable. We don't have, if we want to have the power to provide cooling at so low temperature. So that's the reason why we need to be very careful. And the approach with some customer is to design already at S30 or at 25 degrees Celsius, which might not be enough if these diagrams move even colder in the future. So the main point is to continue the cooperation between all of us, is to continue to integrate the mechanical and electrical companies as Schneider Electric in their journey and cooperation with NVIDIA, but also the entire ecosystem, the end user, the specifier, the consultant, the contractor, to work together in integrating the portfolio that we have here with the design. So the best way to move forward in looking at the cooling for AI is not just offer. It is cooperation, is literature, is reference design, white paper that allow us to share what we know and get feedback from what you got and what you understand and what you define, but also to touch base on the real application at the factory, in the lab, or during the design phase. Thank you. Any question, any comments? Yeah. I think so. I think so. And by the way, part of the document I mentioned here, so the reference design and the white paper are available on the Schneider portal. We may leave you also the link for that. One more white paper is on the way about liquid cooling and sustainability that we are going to release by the end of March. And the one that defines the architecture is already online. We promote these on LinkedIn, and we will give you the link to download. So these presentation will be available, but the detail on the reference design white paper will be available as well, are available as well. Thank you. Very good point.
In all the liquid cooled solutions, is all the materials standardized? There's no gap bank corrosion?
That's, let's say that today, to prevent this, to prevent the corrosion or the challenge on that, all the community is more on the safe side. So propylene glycol 25% in the TCS, 25 micron or lower filtration.